Hello guys! Today, we are going to talk about power factor. We will start really easily with popular beer analogies to help you understand the basics, and then we'll see some examples of good and bad power factor and how to fix bad power factor. So, what exactly is power factor? Imagine you're at a bar ordering a beer. Don't worry, just imagine. You pay for the beer by the glass, but inside that glass, there's both beer and foam. The beer represents our true power or kilowatts, the useful stuff that does the work. The foam, on the other hand, symbolizes reactive power or kilovolt amps reactives, the not so useful stuff that we still have to pay for. When we combine true and reactive power, we get apparent power measured in kilovolt amps. Power factor, then, is the ratio of true power to apparent power, indicating how efficiently we're using the power. In electrical terms, we visualize power factor using a power triangle, where the true power is represented by the adjacent side, reactive power by the opposite side, and the hypotenuse represents the apparent power, forming an angle known as theta. This angle theta indicates the power factor. Residential bills often overlook power factor, but commercial and industrial bills consider it. Poor power factor leads to penalties due to increased current flow, voltage drops, and decreased distribution capacity. Large consumers with bad power factors strain the electricity network. The power factor typically ranges from 0 to 1 because true power is always lower or equal to apparent power. A good power factor is between 0.95 and 1, while a poor power factor is between 0.85 and 0.95, and a bad power factor is below 0.85. Now, let's consider a practical example of power factor. Let's imagine factory A and B, both with a power consumption of 100 kilowatts. Factory A has an apparent power of 104 kVA, while factory B has 116 kVA. Let's calculate the power factor of factory A using the formula power factor equals true power divided by apparent power. So, for factory A, it would be 100 kilowatts by 104 kVA equals 0.96, indicating a good power factor. Similarly, for factory B, it would be 100 kilowatts by 116 kVA equals 0.86. This suggests that factory B is operating on a poorer power factor, which could result in additional costs. Causes of poor power factor. There are three types of loads in electrical systems: resistive, inductive, and capacitive. Resistive loads, such as incandescent lamps and heating elements, consume electrical power in phase with voltage, resulting in a power factor of 1. However, inductive loads, like induction motors and anything that has a coil or winding, cause a phase shift between voltage and current, resulting in a lagging power factor. This means not all of the electricity is being used to do work. Capacitive load is the capacitor itself. This also causes a phase shift between voltage and current, but it produces a leading power factor, which means current leads to voltage, again indicating that not all of the electricity is being used to do work. If we draw a phasor diagram for a purely inductive load and a purely capacitive load, we can see they are opposite to each other. In most cases, bad power factor is caused by high inductive loads in the circuit. To correct this, we add capacitive load, which can be a bank of capacitors, or we can use power factor correction devices. These devices supply the necessary reactive power to the circuit, bringing it closer to 1. That's all guys. Thanks for watching, and don't forget to like and subscribe for more.